Bonjour à tous. Eh bien, c'est encore un plaisir, comme toujours, de vous accueillir ici et puis à distance également. Alors, la prochaine fois, donc ce sera vendredi prochain, donc le 22 octobre, nous aurons le plaisir d'accueillir Cécile Moreau, qui est une chercheuse de Clinatec et qui nous propose de nous parler d'une possible innovation pour la thérapeutique. C'est la lumière, d'utiliser la lumière en particulier pour des maladies comme la maladie de Parkinson. Alors, elle va focaliser sa présentation sur la maladie de Parkinson. Et la question que l'on se pose, c'est que c'est essentiellement de la lumière infrarouge et elle a un effet, mais d'habitude, la lumière infrarouge, c'est un effet de température. Alors, pour savoir ce qu'il en est, je vous invite à venir l'écouter. Et c'est vraiment un très bel espoir qu'elle nous apporte avec les travaux qu'il mène à Clinatec. Maintenant, je vais passer à la langue anglaise, puisqu'aujourd'hui, nous avons le plaisir d'accueillir quelqu'un qui vient de Barcelone. So, hello everybody. So, we have the pleasure today to welcome Josep Puigmartí Luis from the University of Barcelona. And he's a research professor at ICREA. And also he's there. We have the opportunity to welcome him here because he is awarded of an excellence, une chaire d'excellence from the Science Foundation. And since he's here for a few months, here till the end of the year, he give us the pleasure to welcome him here and to talk about microfluidics technologies as an advanced tool for material engineering. So the floor is yours, Josep.
Thank you very much for this nice introduction. And also I would like to thank the Nanoscience Foundation for giving me the opportunity to be here today and to have this close collaboration with good friends. So thank you very much for this. And so today I would like to talk about microfluidic technologies and how these technologies can be used for materials engineering. But I will do that also focusing on my previous research, the research that I did during my PhD. And with this, I would like to explain why in my group we use microfluidic technologies. Okay, so the first thing I would like to mention is that, as you know, we are surrounded by turbulent flows, right? So we have the wind streamlines, but also surface currents, like in the oceans and seas. But we all know also that it's very important to control the fluid streams across scales in order to have functionality in nature. And let me give you an example of that. For example, the muscle contraction, right? How does it happen and why does it work? So if we take this picture here, what you can see is really small pink dots. These are calcium atoms. So calcium atoms, they diffuse, they interact with the troponin there, this protein here, and this interaction allows the contraction of this helical protein. This green is illustrated there in green. So that is tropomyosin. By doing this interaction of the calcium with the troponin, what we have is that the tropomyosin contracts and exposes the actin to the myosin. Because of this, there is the bonding between the actin and the myosin, and this bond is only broken when we have the diffusion of ATP molecules and when ATP molecules interact with the myosin. So by doing this, what we have is the contraction of our muscles. So what is important here is to realize that in order to move our body, we need to have a controlled diffusion of calcium atoms and also of ATP molecules. And we need to control the diffusion of these two entities in time and space to be able to move. But now, if we look at the lab, so I'm an organic chemistry, by the way, so if we look what we do in the lab, what we frequently do is to control the fluid streams. The control is only focused on having turbulent mixing. Why? Because what we want to do with this turbulent mixing is to enhance the kinetics of the reaction. We want the things to react as fast as possible. So as you can see, this is totally different. The conditions that we have in the lab frequently are totally different to the conditions that we have in nature. So the question then is, okay, we want to control fluid flows at the lab scale. How to do that? That's the question. Well, we'll have to look at fluid mechanics. And if you look at fluid mechanics, there is an equation that explains the motion of fluids or viscous fluids. And this is the Navier-Stokes equation. That it's an equation made of partial differential equations. I will not go in details here. But what is important, and I think it's very interesting also, is to see that this follows the Newton's second law. So what you have, it's a mass, the acceleration that equal forces. And if you further develop this equation, what you end up with is with a series of dimensionless numbers. These dimensionless numbers describe the behavior of fluids. So, and here I would like, in the first part of my presentation, to focus on the Reynolds number. So the Reynolds number is the ratio between inertial forces and viscous forces. If I tell you this doesn't mean anything, right? But what is important to realize here is that the Reynolds number is the number that allows us to reach these conditions that I was showing for the muscle contraction, allow us to have a controlled diffusion of regions in time and space. So again, these are only words. So I would like to show you this. But the problem would be that the video that I wanted to show you does not work, but probably you saw it. And this, what you have here, is a container that allows you to have very small Reynolds number. And I will try, but I think it's not working. What you could see here is that when you put 3 different dyes and you start to mix them, you can control the diffusion of the 3 dyes and make them go to the initial state without having any kind of diffusion between them. And this is explained, from the Navier-Stokes equations. When you have low Reynolds number, you can control the diffusion of regions in time and space. So the fluid, the velocity of the fluid streams, it's the same. It's invariant with time. And this comes from the equation, the Navier-Stokes equation. But always when I show this video, people tend not to believe me. This can be explained with with physics if we solve the Navier-Stokes equation. But for me, I'm a bit tired of trying to convince people by doing so. So what I decided to do is to play this movie here. So what you see is the same container now, but looking at the top. Look that the position of the finger changes, because I've been also told that I was playing the movie backwards. So what this really shows you is that under these conditions, this low Reynolds number, what we have is a perfect control over the diffusion of regions in time and space. Okay? So this is what we have at the macro scale. But how do we achieve these conditions in conventional laboratories? Well, the question I think that it's given in the presentation, in the title of my presentation. So what we do in my lab, it's to use microfluidic devices. Why? Because microfluidic devices allow you to have this low Reynolds number, so the viscosity dominates the inertial forces. And I will show this here. So what you have is a microfluidic device. And you have 2 different dyes that, as you see, they are co-flowing inside the microfluidic device without mixing. They will reach the end of the microfluidic device, and they didn't mix. How do we mix them? So that's going to be very easy. We only need to change, as you see here, the flow ratio at the inlet. So now, if we decrease the flow ratio, we allow that this red dye diffuses towards this aqueous stream. This aqueous stream at the very end of the microfluidic device. So this is a clear example showing how we can control the diffusion of regions in time and space using microfluidic technologies. Okay, the question now is, well, you have proved that you have a technology that allows you to have similar conditions to what you wanted to have, like in nature, like for the muscle contraction. What can you do with this in the lab? Well, for answering this question, I would like to look back to the research I was doing during my PhD. So during my PhD, as I said, I'm an organic chemist. What we wanted to have, this is a different example, but we wanted to have a defined structure. So in this example that I illustrated here will be this 2D material. So the first thing that an organic chemist will do is to synthesize molecules that will have functional groups that ideally will then self-organize, generating this 2D material. So how are we going to do that? As I said, the typical thing to do is to use turbulent mixing, so to enhance, the reaction kinetics. And here, as you can see, we have no control over the diffusion, so we have depletion zones. This is not well controlled. Then other things that we are going to change in order to achieve our final goal, that is the formation of this 2D material, is to change the time, the temperature, the pressure, or even the solvent composition. And at the very end, given an energy landscape, what we will reach is the most thermodynamic stable product. So here you have an example. This is basically the work that I did during my PhD. I was working with the tetrathiafulvalene, the TTF. This is a very well-known molecule in molecular electronics. And ideally, what you would like to have is to generate a pi-pi stacking of this molecule, because when it's partially oxidized, it allows conduction of holes through the structure. So this was the things that I was doing during my PhD. So I was changing the functional groups in these positions in order to achieve this pi-pi stacking of the molecule. As you can see here, with a very long alkyl chain, this is the STM image. What you see here brighter is the part of the molecule with the higher electronic density. So what you see here is that the molecule is lying flat on the surface. And this is not what we want. What we want is to have this type of organization here, where the molecules will lie, perpendicular to the surface, where we will have this pi-pi stacking. So how to do that? This is what I told you. As an organic chemist, we'll go to the lab, we put different functional groups, now amides, and now because of the hydrogen bonding, what we can achieve is this perfect organization of the molecule on the surface, which is now organized perpendicular to the surface. Okay? And this can be clearly seen here. So here molecules are lying flat, and here they are tilted with respect to the surface. Okay, so now that we have this in mind, let's see what happens when we use microfluidic technologies. The same molecule, but note that here we don't have any functionality. It's the bare molecule. We oxidize it with a gold salt, so the gold will reduce, and we expect to have this pi-pi stacking of the molecule. What we are changing now here is the flow rate ratio that is defined between the ratio of the seed flows, these blue flows here, A and D, divided by B and C, which are the reagents, the TTF and the gold salt. So if we do the reaction with microfluidics at very low flow rate ratios, so in this condition here, what we have is a mixture of crystals. This is what you see there. So there is no defined morphology. But look what happens when we increase the flow rate ratio. We are changing the morphology of the material. But not only that, if we do diffraction, what we also change is the pi-pi stacking distance of these TTF molecules in the final structure. So this is a clear example that hydrodynamic flows controlling the fluid streams that I was talking at the beginning can have a tremendous impact in the final product that you will generate. And this is clearly seen here. If you remember the previous slide, in order to change the structure, I always needed to change the functional groups in these positions. Here, I'm not changing the molecular building blocks. They are the same. The only thing that changes is the conditions in which they are interacting. Okay? So this is another example. This is another porous coordination polymer. So in that case, you know, if we do the reaction in bulk, we have these square plate crystals. So the idea here was, okay, what will happen if, again, we do the synthesis changing the flow rate ratio? So what you see is that at really low flow rate ratios, we have the same kind of crystals. But now, if we start to increase the flow rate ratio, we go through a series of intermediate states that have the same diffraction pattern, but that you cannot obtain in bulk synthesis, even when you are surfactants. So what this allows us, this controlled reaction in microfluidics, because we can control the diffusion of these two regions in time and space, we are capable of freezing the crystallization process. So we can isolate states that are intermediate states towards the final thermodynamic product that is this one here. Recently in the group, so what we were asking ourselves is, okay, so we have shown that we can stop in a given pathway, assembly pathway, we can stop at intermediate states. But the question is, given an energy landscape, can we go through different pathways than the thermodynamic one? Can we unveil other pathways? Well, this is a whole research area. It's the mesoscale assembly, right? So the non-classical nucleation theory. So there are people that they say, look, to generate a final thermodynamic product, this can also occur following not the classical nucleation theory, but it can happen isolating intermediates, like for instance, nanocrystals that then they will, by particle attachment, assemble and generate the final thermodynamic product. Here, you know, this kind of research is, for instance, being very much studied by Professor Helmut Kolfen at the University of Constance and Stephen Mann, also Professor Stephen Mann. So they are trying to prove that there are other pathways that the system can follow in order to reach a final thermodynamic product. But here I also believe that these intermediate spaces, sorry, it's not, yeah. So these intermediate spaces can also lead you to different products than the thermodynamic one. This is also what I think, and this is very interesting because these new products could have different functionalities, okay? So what we did here, so it was to do the synthesis of this spin crossover, which is also porous, so you see that can embed up to two CO2 molecules. This is a collaboration with Guillermo Mínguez at the University of Valencia and Eugenio Coronado. And what we did here was the synthesis of this spin crossover with microfluidics. Now here we fix the flow rate, and what we observe is that from 0 to 6 hours, we have this kind of crystal growth. So we have also the formation of the hexagon. Like, sorry, let me show you that if you do the reaction in bulk, what you have is this hexagon as a thermodynamic product. So when we do the reaction with microfluidics, what we see is we have an hexagon, but this hexagon is growing from the vertices of the inner one. But then from 6 hours to 12, it looks like now the hexagons are growing from the face, not anymore from the vertices. So what we thought when we observed that is that given the energy landscape, this is the thermodynamic pathway, right, that allows you the formation of this hexagon. So there are other two pathways that we are unveiling by doing the reaction in this controlled reaction diffusion conditions that we have in the microfluidic device. So how do we think, or why do we think that the vertex is favored versus the phase one? So if we look at the crystal structure, what we see is that the interactions here are ionic interactions. And these ones are via van der Waals interactions. So this is why we think that the vertex is powered, because the interaction is stronger than the van der Waals ones. But, you know, when we submitted this manuscript, one of the reviewers told us that what we were observing, it was just an artifact. And they didn't believe these results. So we needed to further corroborate the results by doing numerical simulations. And this is what we did here. So what you see is full atom molecular dynamic simulation experiments, where we have 10 strands of this coordination polymer. And in the center, we generate a cluster of these strands made of up to 19 strands, okay? We position these 10 like 1 nanometer far away from this center one, so that we are completely sure that the system is unbiased. And what we see is that if you see the blue dots here, this will be the growth from the vertex, whereas the green will be from the face. And what you see is that if you look at the density and distance, is that in fact, the growth is initially favored from the vertices. So this clearly confirms the experimental data that we obtained, okay? So another important fact here is that with microfluidics, we can isolate the nucleation species because we can collect whatever is generated in few milliseconds in a TEM grid after the synthesis in the microfluidic device. Whereas in the bulk, as you see, while in microfluidics we could observe these small particles, in bulk we could never observe anything at time 0. So if we check the bulk synthesis, we were very surprised to see this mesoscale assembly. So as you see here, we have a small hexagonal crystallites that they assemble to generate the final hexagonal crystal structure. And this was very interesting because it was the first example reported in the literature showing this mesoscale assembly for the formation of this of a spin crossover compound. So this is what we observe. So with microfluidics, we can unveil these two different pathways that at the same time are different from the thermodynamic one. Okay, so now here, I always get a question, or frequently people tend to ask me a question that it really makes me mad. So I'm gonna ask my question now here because I would not like to get the question from the audience, okay? And the question is, people ask me, okay, what will happen if you change the solvent? Well, if I change the solvent, I'm going to change the energy landscape. What I want to prove here is that given the same conditions that I have in turbulent mixing in a lab, using the same conditions of temperature, humidity, everything the same, but changing the control diffusion in time and space, I can unveil different pathways. This is why changing the solvent doesn't make sense, because I will change the energy landscape. What I want to have is the same energy landscape and see the effect of this microfluidic mixing, okay? And this is what we observe here, that when you do that, you are capable to go through pathways that you will never achieve in bulk synthesis. Okay, so as I shown at the beginning, there are other dimensionless numbers that, I mean, here I only listed a few of them, but we recently started to work also with the Grashof number. What is the Grashof number? Well, the Grashof number is a ratio between the buoyancy forces and viscous forces. What does this allow? Okay, there are two questions here that we need to answer. How to achieve low Grashof numbers with microfluidic technologies, and what this will allow us to do. Well, how we do it? So there are different devices that we are working with. Here I will give you the first one that we started to work with, and this is the device. So you see it's a two-layer device. So you have a top layer that is used to control the fluid flows in the bottom one. So like in this example, this movie here, what you see is that, yeah, we have the top layers that are valves that are initially closed. Then we close the two on the sides and open the middle one. And the idea here was to see if we could have a free diffusion process, okay? So a process where we will not have convection or any other problematic fluid behavior, okay? So what we want to have is a free interface diffusion process. So as you see there, I mean, the blue and the yellow completely diffuse, and they generate the green color in the whole area of the reaction. But we could not see what was happening really at the interface. This is why we use this imidazole derivative and reacted it with zinc, because it generates a fluorescent coordination polymer. So what you see here is now this reactor there. This is the valve. So as soon as we open the valve, we see that we generate this fluorescent coordination polymer really at the interface of the two liquids. And then because the diffusion coefficient of zinc is higher, so we have the zinc that diffuses more towards this imidazole derivative. So this clearly proves that these devices allow us to have a free interface diffusion process. So then the question here is, okay, so if we have this free interface diffusion process, can we use this, for instance, for shaping crystals? So as you know, this is a MOF crystal. So in that case, we cannot control how to grow the crystal. I mean, the growth, it's given by the crystallographic information that the crystal has. So the phases with the higher surface energy will be the phases that will grow faster, right? And we cannot change that. So the idea was, again, now to use this peptide-based MOF and do the synthesis in these microfluidic devices that I've shown before. And what you can see here is that we can see perfectly how these MOF crystals are growing. But not only that, what we can do is, via a segmentation algorithm, what we can do is to follow the growth and study the kinetics of the growth. We did also a mathematical model that allows us to model the data that we are observing experimentally. And as you see, our model fits quite well to the kinetics of the growth. One thing that we are not controlling, though, is the nucleation. This is why we have these different lag times. We can control where we grow the crystal, but we cannot control the exact position where the nucleation will start. Okay, so this is something that I think will be very interesting to look at as well. So what we can do, as you see, is if we work above this 100 millimolar concentration, what we can do is to continuously grow the crystal. But if we are below this concentration, we can dissolve it. And this is what you see there. So, and this is very, very interesting, because this is completely different to what we have in conventional laboratories. So there the crystal will grow, as I said, following the crystallographic information. And we are not able to, provide the crystal with new mass to grow as we want. Here, in these conditions, in these free interface diffusion processes, we are able to keep the system always out of equilibrium, because we are constantly adding mass to the crystal. So what this allows us to do then is to, if we add new nutrient here, we will accelerate the growth of the crystal. If by doing so, what we can do is very complex structures with these MOF crystals. So as you can see also here, this is a single crystal, and of course, this is a shape that you will not be able to generate in a conventional laboratory conditions. Of course, one thing, this is work that we did while my group was there at ETH, and I asked the student, who, please grow a crystal with a very complex shape. And then he came up with this idea. This is normally what happens when you are at ETH. People tend to have the ETH logo everywhere. And, and he was really disappointed, And he said, look, but I managed to get this, but this is not a single crystal. Well, and my answer was like, yeah, life, it's not easy, right? But look at this here. I mean, you playing with the microfluidic device and the fluidics, we were able to generate single crystals that were millimeters in length. So this is a remarkable finding. And as you see, now we don't have anymore this polyhedral shape. So what we have here is what you see, this semicircle shape of the MOF crystal. So then, if we change the microfluidic device, we can also change the shape of the crystal. And we can, for instance, generate as you see here, films. Okay, so this was a very interesting topic, and we are continuing working on that. So we were also very happy to get the cover of the journal. And something that we are focusing now is also in 2D materials and trying to synthesize them in these conditions, okay? So here, an example, this is a very well-studied conductive MOF, or 2D MOF. And what it happens is it's very difficult to generate very long, thin films with this material, okay? So normally people are using pelletization to get pellets and do the measurement. It's very difficult to grow them over long distances. And the method that people normally use is this one here, is a droplet that is exposed to the different regions in order to create the precipitation. But what happens here is that you have the formation of this convection. So imagine that we generate a crystal here, the crystal will fall, and this will generate even larger convections, okay? And as you see, the diffusion is in favor of gravity. We, fabricated this microfluidic device that allow us to have this low Grashof number. And a low Grashof number is what you have in the International Space Station. So this is known. Many companies are trying to crystallize proteins there because you have this free environment of convection to, generate crystals of proteins. So what the Grashof number that we have here is very similar to what you will expect in this International Space Station. And what you see here is that while here the diffusion front goes in favor of gravity, in our case, it goes perpendicular. So it's like we are simulating microgravity conditions there. So doing that, what we observe is that now we can grow a really large film with this 2D conductive MOF. So this is also very important to mention. So because this is so large, we can measure this crystal in all directions. This is the previous literature. This is our work, and this is the previous literature. So you see that we measure our films in ambient conditions. So we have the highest conductivity reported. The only one that it's also done in ambient is this one here. But there they applied 1 gigapascal to get this conductivity. In our case, we don't apply any pressure. We just take the film that we generated in this simulating microgravity and measure it. We can measure it in all directions. Okay. What we also did is, if you do the synthesis of covalent organic frameworks, if you do the synthesis again, we use the same conditions in the lab that we use in the lab. We will use them in this other microfluidic device. If we do the synthesis in the lab, what we have is the formation of these microcrystalline particles of the COF. But if we do the synthesis under this simulated microgravity using the same conditions, only the controlled diffusion that I've shown before, we have the perfect formation of these really long unextended COF films. So this clearly shows you that this simulated microgravity, what allows you to do is also to control morphogenesis. And that's a very nice finding. So we are still working on this. And of course, that's the idea of the student. So we were lucky also to get the front cover of the journal. So and when she showed me this idea, I really like it. So to have this astronaut there inside the microfluidic device. So, and this is a video showing how easy it is with this methodology to, place these COF films in any other substrate, okay? So you see that we can generate them and then transfer them very easily. Finally, and these are gonna be my last slides, I will like to also show you what we are recently doing with the group of Professor Brad Nelson and Professor Salvador Pané at ETH. So this work that we do in my group now, it's in collaboration with this good friend of mine, Professor Salvador Pané, and it came all from a discussion that we had in 2015 in a conference. So you probably know, Professor Brad Nelson, he was there is a law that I'm sure that you all know, the Purcell's law, the scallop theorem. So that it says that a really small scallop at the nanometer scale, it will not, have motion because of the low Reynolds number. And this is something that I could not show you, but you could have seen in the video that didn't work. So it will always, move to the initial position, and this is the scallop theorem. So the only way to overcome this problem is breaking symmetry. And this is exactly what Professor Nelson did in the field. So he invented these helices, and with these helices, you can break symmetry and have motion, direct motion. So the idea here was to combine this MOF chemistry with micro and nano robotics. So what we did is to grow these MOF crystals on top of the micro nano robots that Professor Salvador Pané is developing in his group. And then we can control the motion of these robots. You can see here, we can position them in different directions, so we can move them in 3D. So one thing we did, it was like you will see in this video here, is the MOFs here, they are embedding rhodanine B, so we can direct them in a cell culture and position them in the cell that we want to do the drug delivery, okay? So this is what you see there. They went out of focus, but now back to focus. So, and in here, what you can see is that we can direct these micro nano robots to the position that we want in the cell culture. So then what we also did is to prove that microfluidic devices can be used to generate phantom environments. For instance, it's known that these MOF crystals can dissolve at acid conditions. So we created areas of the microfluidic device that were at pH 5, where the MOF will dissolve. And here you see we have 4 micro robots. So all of them have the rhodamine on it. So when we move 2 of them to pH 5, the MOF dissolve. This is why they lose the fluorescence. And then we can move them backwards to pH 7, where the 2 that stayed there are still fluorescent, but these 2, they lost the cargo because they went to the area that was a lower pH. This had a very big impact in the field. It was highlighted in CIEN. And we also were very happy to do this work in collaboration with the group of Professor Shuhei Furukawa at Kyoto University. This is why we did this cover with manga drawing. So with that, I would like to thank you very much for your attention, and thanks again to the Nanoscience Foundation for allowing me to be here in this great place, and thank you for your attention.
Thank you very much. Thank you. Thank you. It's amazing. Okay, so your presentation is open for the questions. So we are going to ask for questions. Have you any questions in the? They may be asked in French, and my colleague David will translate it. Okay, we have a question from the.
Thank you very much, Josep. Very nice presentation. I just have a curiosity. So you are able to do very nice single crystals within your microfluidic device. How easy is it then to take them out from there? Do you break the device? How does that work?
Yeah, I mean, from the mechanical point of view or the engineering point of view, it's very easy. So we can unbond the chips and take them out. But then it's a matter of the fragility of the crystal. In this case, these are, like soft MOFs. So they are made of peptides, so really long molecules. They are very flexible. So they tend to break sometimes when you open the microfluidic device. But it's only a matter of the fragility of the crystal that you work with. Okay. But it's possible to, I mean, in this work, we took them out, we measured single crystals, so that's something that it's possible, yeah.
Okay. And if I may, a second question, is that okay? Yeah.
So you're welcome.
Okay. So how do you build these microfluidic devices? Could you explain just a little bit?
So frequently use polydimethylsiloxane, so PDMS. And what you need to have is a master mold made of silicon wafer. So you need photolithography, and then we do the casting molding. So there is a good paper by Whiteside's group explaining how to assemble these devices. And now we are also trying to work with other materials, like for instance in this 2D we work with Teflon. In collaboration with David, we are also using glass or even polymer. So the answer is we can work with a lot of different materials depending on the solvents that you are going to be using for the synthesis.
Okay, great. Thank you very much.
Thank you. Yeah, you're welcome.
Yes. Did you see an influence of the shape ratio of the channels on your fabrication of crystals?
Sorry, I missed the...
Yes. Did you see an influence of the shape ratio?
Okay.
Highest
hauteur.
Yeah.
Yeah.
Yeah. This is a very interesting question. So, and that's something that I'm looking at right now. So the shape of the channel will define how these interfaces are built. And this, I believe, will have an impact on whatever you produce. So we tend to always use the same aspect ratios, also because from the fabrication point of view, we have all the methods like standardized, so it's very easy for us to produce these devices. But I fully agree that looking at this, it's also a very, very interesting topic.
Thank you. So we have a question from the people that are on the video conference. Please, yeah. So, David, would you please? Oh, do you want me to ask the question? Yeah. Okay.
Hello. Do you think that your work can help understanding wettability issues between a polymer, epoxy, for example, and a surface of silicon, glass, or oxides that we use in the microelectronic research?
Sorry, if epoxy can help, or what?
If you help understanding wettability issues between a polymer, epoxy, for example, and a surface of silicon, glass, or oxides that we use in the microelectronic research.
So wettability is something that in my group we are not looking at. So, but if I got the question well, I think that looking at how flows will interact with different surfaces, it's something that you definitely could look at using microfluidic devices. Yeah. So, for instance, I'm aware of people using digital microfluidics, so where they have electrodes and they move, changing the electric fields. They can, move and mix solvents at ambient conditions. So that's, yeah, I think that could be of help. Yeah.
Okay, thank you. We have still one question from the room.
Thanks, Josep, for this magnificent results you have accumulated.
Thank you.
And I have a question about the configuration of the glass of small numbers. When you have this interface, you start the diffusion. So you start with the instability of the interface. So can you give some numbers about, for example, this length scale where the instability is developed, how it is correlated to the difference of speed rate? And have you some grain-field instability in this interface?
Yeah. So that's a very good question. And one of the reviewers of the paper really asked us that. So the question there was, okay, so you show that you can have the diffusion, going against gravity. So what will happen if now you consider the same size of the droplet that we did in the simulations and use it in your microfluidic device? And there, we didn't run that simulation, and we did for the reviewer. And what you see is that if you increase the height of the channel, then the diffusion goes in favor of gravity. So it's only, there is a tiny, range of dimensions that will allow you to have these simulated microgravity conditions. So, and how the diffusion will occur, it will be based on the diffusion coefficient of the regions that you are using for the synthesis. But yeah, this is, I was very, I mean, we tend to complain about reviewers, but this time, it was very useful, this question, because it really allowed us to prove that it's really the microfluid device that allows you to have this simulated microgravity condition.
Thanks.
Okay, thank you very much. Is there any other question? Yeah, we have still one other question from the room.
Thank you for the presentation. And I wanted to ask you if you already investigated the possibility of depositing several layers of different materials. So, like also about the first question that was asked before, if you may grow a sacrificial layer and then your single crystal, and then after to remove your single crystal from the substrate, you can dissolve the sacrificial layer, or maybe also like growing multi-layer materials for some advanced application.
Yeah, very good question. And we are actually looking at this to generate heterostructures. That's a very good point. Yeah, so we are working on this now, and this platform is an ideal platform for doing this as well. So we are looking at this. About the sacrificial layer, I mean, if you think about the covalent organic framework film that I've shown here, it's very easy for us to to take it out of the surface and to transfer it anywhere. So that platform is ideal for that. But that's true, it's not the same in the case of this 2D MOF. So there, it's very easy to remove the layer from the, we are trying to do this, but it's not that easy. So, but yeah, for the generating or synthesizing heterostructures, yeah, that's a very good point.
Very much.
So thank you very much. I think that we have reached the end of our presentation. So thank you again,
thank you,
Professor,
thank you
for your presentation. Very nice presentation, and we wish you the best for the next for your next work.
Thank you.
Okay. Bon, je vais switcher en français et donc vous inviter donc à nous rejoindre la semaine prochaine pour écouter Cécile Moreau. Et donc juste une petite chose, c'est qu'on n'a pas la possibilité d'utiliser l'amphi la prochaine fois. Et donc, le prochain Midi MINATEC sera entièrement en distance. C'est dommage, mais c'est comme ça. C'est la vie. Et donc, on espère bien qu'après, vous reviendrez nous rejoindre parce que on va pouvoir vous accueillir beaucoup plus nombreux dans cet amphi. Donc, à bientôt. Et j'espère vous retrouver la semaine prochaine pour écouter Cécile Moreau.